Energy from vacuum. According to quantum mechanics, empty space is not truly empty, but virtual particles pop in and out of existence, constantly creating and annihilating each other. Furthermore, entangled particles, such as a pair of photons or electrons, remain connected even when separated by vast distances. Japanese scientist Masahiro Hata predicted that entanglement should make it possible to harvest the energy at a distance. The process was recently proven by two independent groups of scientists. So how does distant energy harvesting work? How can energy translocate in space without the need for physical transport? And what is the correct intuition of quantum mechanics anyway? To answer these questions, we start our investigation with gravity. Gravitation remains one of the least understood physical phenomena. According to Mach's principle, a motion may only be defined relative to other objects. The quantity and distribution of matter in the universe determines local movement. In practice, Earth gravity dominates our lives, but according to Mach, we should extend our calculations to include the Sun, the Milky Way, and the rest of the universe as well. In developing relativity, Einstein tried to follow Mach's principle, but his final theory failed Mach's requirement. General relativity's famous slogan is attributed to John Wheeler. Space-time tells matter how to move, and matter tells space-time how to curve. The first part of the statement refers to the curvature of the space-time manifold, but the second part relates to particle behavior, which is governed by quantum mechanics. Quantum mechanics and gravity famously cannot get along because the particles of gravity form infinite terms in the calculations. Quantum superposition represents reversible time directions, but in the macroscopic world, time is intrinsically asymmetric, flowing from past to the future. A quantum particle can be in two places at once via entanglement, which introduces a problem for general relativity. Gravity cannot handle uncertain curvature, especially happening at two distinct points of space at once. How can space-time give rise to the divergent behaviors of gravity and quantum mechanics? I propose that the fabric of space is formulated by two separate systems, segregating a discrete wave function from the continuous gravity field would produce two independent systems, the discrete wave function and the smoothly changing field curvature. insulation with an information blocking horizon ensures the wave function's unique dynamics independent from the gravity field. Although energy conservation would dictate that the wave function must associate with identical curvature regions, it is free from gravity's influence. Therefore, it can form entanglement independent of distance and maintain time reversibility. The laws of quantum mechanics are indifferent to the direction of time, but interaction with the field introduces directionality with inputs at earlier times and subsequent outputs. In other words, the symmetric quantum level process acquires classical irreversibility via decoherence. Therefore, time is the tick-tock of the wave function's evolution, which is registered by the smooth changes of field curvature. We can imagine the cosmos as a clock, where the wave function is the big hand and the gravity field curvature represents the small hand, measuring the flow of time. The fundamental incompatibility of general relativity and quantum mechanics might originate in their orthogonal manifestations. The recently proven quantum energy teleportation is a particular case of entanglement that can transfer energy from one location to another without physical transport. The wave function in the bottom of the drawing as interaction with the field changes the curvature, it initiates classical local behavior. The superposition of two energy states allows the harvesting of a tiny amount of energy at a distant location. Consequently, quantum teleportation may challenge local energy conservation, but not global energy conservation. If we go back to Wheeler's famous quote, the second part, matter tells spacetime how to curve, may originate in the wave function, representing the gravity field's energy allocation system. In the economy, loans and investment can reallocate money to jumpstart businesses and technology. Likewise, the transposition of energy over significant distances by entanglement can formulate not only planets and stars, but also cosmic voids. Therefore, the evolution of the cosmos represents an increasing structural organization, which is also true for our own cosmic neighborhood. However, if gravity were to dominate spatial dynamics, globular galaxy aggregates would squeeze vacuum into the corners. That's not what we see. The global organization is dominated by the expansion of empty space. Energy transfer via entanglement supports the formation of spherical cosmic voids with overdense ridges. Interaction produces orthogonality, where the wave function tells the field how to curve, and the field tells the wave function when to decohere. Therefore, inertia is proportional to the field strength, an apparent necessary condition for satisfying Mach's principle. An object's position corresponds to a freely hanging plum. Deviations in the angle of that plum, location of the object, change the equilibrium of the whole universe and lead to inertia. Inertia is proportional to the field strength, which is the topological distance from the black hole. Thus, test particle mass increases in the vicinity of a large mass, such as a black hole. Inertia reflects the whole universe field structure and global dynamics, as Max insisted. In conclusion, space-time is not a singular physical structure, but consists of a discrete wave function and a separate continuous gravity field. The result is a wave function without spatial limitation, which makes entanglement and reversibility possible. However, decoherence or interaction is an irreversible transformation, which transfers the energy to the field, modifying its curvature. Therefore, the field's smooth fabric can transmit gravitational waves and engender a temporal evolution. The universe's complex global organization requires the antipodal dynamic of quantum mechanics and general relativity. Entanglement and decoherence underlie cosmic regulation by their antipodal push and pull, shaping cosmic topology and the global energy budget. One, it constricts cosmic behavior to fine-tune its parameters and lead to the direction of time. And two, it satisfies Mach's principle.